Hello everyone. In this lecture, I'll first give a brief sketch about the origin of hyperbolic geometry, and then I'll tell you about the core summary and essential details about it. So let us begin. So this hyperbolic geometry is a part of this non-Euclidean geometry. So to understand hyperbolic geometry, so first you have to understand this Euclidean geometry. So this Euclidean geometry we have done in schools. So first let us go through the Euclidean geometry. So this Euclidean geometry, it is due to the ancient Greek mathematician Euclid. So this Euclidean geometry, it is the study of plane and solid figures on the basis of axioms developed by Euclid. So this Euclid described his work on geometry in his famous textbook, The Elements. So according to Euclid, so a point is something which has no part, and a line is breadthless length, and the ends of the lines are points. And a straight line is a line which lies equally in with respect to the points on itself. So these definitions are completely vague, and it is based on our natural intuitions. Okay, so similarly, surfaces, angles, circles, etc. are defined. So this Euclidean geometry is based on 5 axioms given by Euclid. So what is the first axiom? So if you are given 2 points, you can draw a straight line between them. So the first axioms tell that to draw a straight line from any point to any point. The second axiom, it states that to produce a finite straight line continuously in a straight line. And the third axiom is it states that so given any point, you can treat it as a center and a distance. You can construct a circle with that point to be the center and that distance to be your radius. And the fourth axiom states that so all right angles are equal to one another. Okay, so the fifth axiom, so now let us move to the fifth axiom. So this is the most important axiom. So it is called parallel postulate. So it says the following. So if sum of interior angles alpha beta is less than 180 degree, so then so you first start with 2 lines L and M. So the picture is given here. You start with the line L and M, and you draw this line N, which intersect L and M, and you take the interior angles alpha and beta. So if sum of interior angles alpha and beta is less than 180 degree, so then this L and M meet when produced indefinitely. Okay, so this L and M will intersect at some point if sum of this alpha and beta is less than 180 degree. So equivalent formulation of parallel postulate is given by Playfair. So it says that given a point and a straight line L on a plane with P not lying on L, so there exists a unique bi-infinite straight line passing through P and not intersecting that line L. So this is an equivalent formation of this parallel postulate. So this fifth postulate appeared to be very unnatural for mathematicians earlier, and they tried to prove the fifth postulate using the other 4 postulates. But each time they have to assume some additional things to conclude the fifth axiom. So this attempt continued for 2000 years. So until in 19th century, around 1830, mathematician Gauss, Nikolai Lobachevsky, John Boole came up independently with a geometry violating the parallel postulate of Euclidean geometry. So here, so they found a geometry So there exist infinitely many straight lines passing through P and not intersecting L. So this geometry was called to be hyperbolic geometry. So we have talked about this Euclidean axioms given by Euclid, and so let us give a model for this Euclidean plane, so where those axioms will hold. And now here, this you can have a clear definition of this point, straight lines, distance, again angles, circles. Okay, so this already you have seen in the school. So this is called analytic geometry. It is given by Descartes for Fermat in around 1637. Okay, so first of all, so take the plane R2. So it is the ordered pair x comma y, where this x and y both are real numbers. And now define distance between 2 points. Let us take 2 points x1, y1 and x2, y2, and define the distance to be equal to root over x1 minus x2 whole square plus y1 minus y2 whole square. So this distance is called Euclidean distance. And what is the meaning of straight line? So you take a map alpha from any interval to R. So what is this map alpha? It is just the convex combination of these 2 points x1, y1 and x2, y2. Okay, so that is alpha t is equal to your 1 minus t multiplied by x1, y1 plus t times x2, y2. Okay, so similarly, we have notion of circles also. And this angles, you can define in terms of inner product. So what is an inner product in R2? So you take in again two vectors x1, y1 and x2, y2. So the inner product is defined to be equal to x1, x2 plus y1, y2. So using this inner product, you can define norms. And so using this inner product and norms, you can define the angles between two vectors. Okay, so here easy to check that. So all the Euclidean axioms are true. Okay, so now given any differentiable path in R2, so how to compute the length of that path? So that you can do it by this metric. So ds square is equal to dx square plus dy square. Okay, so suppose you are given a path alpha from this closed interval AB to your R2. So you can compute the Euclidean length. So alpha t, suppose it is xt comma yt. So length of alpha, it is integration a to b dx dt root over dx dt whole square plus dy dt whole square dt. So given this formula, you can compute the length of any differentiable path in this Euclidean plane R2. Okay, so now we have given a model for the Euclidean plane, and now we will produce a model for hyperbolic plane. Okay, where the axioms of this hyperbolic geometry will hold. So you start with this upper half plane. So upper half plane means you take the order triple x comma y in R2 and take y to be greater than 0. And again, you put this formula here, ds square is equal to your dx square plus dy square by divided by y square. Yeah, so we'll do all this thing in details for a deep sketch. I am writing this thing. So given this formula, again, if you take any differentiable path in alpha, so you can compute the length of that path alpha. Okay, so using this formula. So this formula, I'll call it to be hyperbolic metric. So we'll all do all this thing in details. Don't worry about it. Okay, so here straight lines, now it will be replaced by geodesics. Okay, so now what is the meaning of geodesics? So geodesics are paths of shortest length. So one can prove that. So geodesics in this hyperbolic plane with this hyperbolic metric, are vertical lines and semicircular arcs with centers on real axis. Okay, so this picture I have drawn here. So this vertical line here, it is a geodesic. And if I take any semicircle with center on real axis, so this will be also a geodesic. Now here you can check that this violates the fifth postulate of the Euclidean geometry. Okay, so you first take a point in this upper half plane and you take a geodesic L. So you take a geodesic L which does not intersect this P. So P is not on this L. Okay, now through this P you can have this vertical line and you can have many semicircles whose center lies on this real axis and it does not intersect the given line L. So in fact, there exist infinitely many geodesics passing through P which does not intersect this L. So this clearly it violates the fifth postulate of the Euclidean geometry. Okay, so now that why this hyperbolic geometry it is interesting. Okay, so let me ask you this question. So find a simply connected metric space of constant curvature. So if you have learned about fundamental group, so simply connected means that so a topological space is said to be simply connected, but it's path connected and its fundamental group is trivial. Okay, and so if you have done a little bit of surface geometry, maybe you know the notion of curvature here. So curvature means here, so bending of the surface, okay, bending of the space. Okay, so here, the question is, so find simply connected some surface of constant curvature. So for example, so if I take this R2, so that is your this Euclidean plane. So Euclidean plane is flat, means curvature at each point is, so Euclidean plane is flat, means curvature at each point is 0. So this means that it is a constant curvature surface. And if I take unit sphere, it is embedded in your R3. So it has, one can prove that it has curvature +1 at each point. So it is a constant curvature surface. So we have now two things. So if I take 0, so Euclidean plane, it has curvature 0 at each point. And if I take unit sphere, it has curvature +1 at each point. Okay, so now what about this hyperbolic plane? So hyperbolic plane, again, it means that upper half plane with hyperbolic metric. So this is a little bit difficult task. So one can prove that it has curvature -1 at each point. So this cannot be visualized. So again, whenever I say that it cannot be visualized, so I have to make sense of it. So Hilbert, the great mathematician Hilbert, he proved that so hyperbolic plane cannot be isometrically embedded in R3. So visualization means, so anything which is embedded in R3, so that is the meaning of visualization as per me. So Hilbert proved that hyperbolic plane cannot be isometrically embedded in R3. Yeah, so in this course, we cannot prove this thing. So this is very difficult. Yeah. So now let us pass to next question. So find surfaces. So what are surfaces? So surfaces are just two-dimensional manifold. So find surfaces of constant curvature. Okay. So again, one can prove that. So if you take torus, it is S1 cross S1 you can think. So it admits a metric such that curvature at each point is 0. Okay, so torus, it admits a metric. So, and this metric will definitely come from the Euclidean plane. So torus admits a metric such that curvature at each point is 0. Okay, and now you take G greater than equals to 2, and let us take, so G connected sum of this torus. So this is torus connected sum, torus connected sum, torus. Take G copies. So one can prove that, so this we'll be doing in the course. So this torus admits a hyperbolic metric. Okay, so one can prove that for G greater than equals to 2, so this G connected sum of torus, uh, it admits a hyperbolic metric. So one can prove that there exists a covering map from this upper half plane to this surface, and you can push the metric of the hyperbolic plane to this G connected sum of torus. Okay, so once you can do that thing, so then the curvature at each point of the surface will be -1. Okay, so now let us tell you about the course summary and what we'll get from this course. So regarding the basics, so complex analysis, topology, and little bit algebra, group theory will be needed. So in complex analysis, we'll need Mobius transformation, cross ratio, Cauchy-Riemann equations, and also this holomorphic functions. And little bit of algebraic topology will be also needed. So where fundamental group, computing maps. So this will be also needed. And so what I'll do, so whenever it is required, I'll cover that thing. Okay. Yeah. And next, so regarding hyperbolic geometry, so we'll be discussing about various models of this hyperbolic space. So I have discussed about upper half plane model. There is another model, unit disk model with Poincare metric. We discussed about the hyperbolic inner product, geodesics, isometry groups, classification of isometries, area of triangles, and trigonometric identities. So then we'll again do some topology. So this properly discontinuous action, co-compact action, Gaussian group covering space, fundamental region, tessellation of this upper half plane, and some algebraic properties of Gaussian groups. And then we'll introduce hyperbolic surfaces, and we'll state the Poincare's theorem only. And later on, so we'll study about the closed curve and closed geodesics in hyperbolic surfaces. So once we have done this thing, so then we'll move to application of this hyperbolic geometry in metric spaces or in group theory. So we'll introduce hyperbolic groups. So in order to define hyperbolic groups, we should have the notion of the slim and thin triangles, delta hyperbolic metric space. And so we'll prove that in hyperbolic metric space, geodesic diverge exponentially. So that is called to be exponential divergence. We'll define quasi-geodesics and then prove the stability of quasi-geodesics. And then we'll define hyperbolic groups and state some of its properties. We'll do the Watt problem, conjugacy problem. We'll prove that this Watt problem and conjugacy problems are solvable in the hyperbolic group. And references for this course. So for the hyperbolic geometry part, you can refer to the book Gaussian Group by Katok. You can also follow the book by Benedetti Petronio, Lectures on Hyperbolic Geometry. And the third one, this is a note by Bowditch. This you can get in the internet. Yeah, so this note, the title of this note is A Course on Geometric Group Theory. And for the hyperbolic group part, so we'll follow this book by Britson Hepliger. So the title of this book is Metric Spaces of Non-Positive Curvature. So duration of this course will be 12 weeks. And again, so the prerequisites for this thing is topology, basic algebra means only will be requiring group theory, and basic complex analysis. Thank you.